Okay, we're going to take a look at the vector right now. In the vector, we have this set up right here. And then most importantly is we have to understand where is the head, where is the tail for the vector. Now, anything that is the tail, let me write this down. A tail is going to be no arrow. Usually it's going to be a solid dot. And then the head, which is where it's going to with the arrow direction. So here, first thing, observe that this is arrow right here. So that means that I'm going to the lower left direction for my vector 3. And then I notice that there's an arrow right here. That means I'm also going to the lower left for vector 4. And then I'm going to have an arrow right here. This is upper right for vector number 1. And then I'm going to the lower left for vector number 2. Lower right to vector number 5. Now, there are 5 different vectors, and I want to talk about their relationship to each other. First thing, let's analyze that. What are the vectors here? So first thing, let's take a look at vector number 1. Vector number 1, I'm actually starting from -2, -2 to 3, -1. Now, how does that actually work? Well, I'm actually traveling to the right and I'm going up eventually. So in here, going from -2 to 3, I actually move 5 to my right direction. So 5 to the right. Let me put a tiny note right here. And then I'm at -2 going up to a -1. That means I move one unit up right here, 1 up. Now, how do I put it in the vector notation? I'm going to put 2 V-shaped bracket right here. And then if you want to represent it in a component form, which is going to be 5I with a tiny hat plus 1J with a tiny hat. Sometimes you just put plus J. Either way it will work. So this is going to be a 2 different representations for the same exact vector. So that means I don't actually have to put my V1 right here. I can have a V1 right here. So I'm going to have 5 to the right, and then I'm going to have 1 up. So which is right here. This is going to be another V1. I can put V1 somewhere else also. Right here. I'm going to do that. That's also a good V1. Now again, all vectors are movable. They're just telling you that I have the exact same length and then the same angle direction opening up. Okay? They don't always have to place in the same exact location. All vectors are movable. You can build it on top of each other. That's perfectly okay. Now, based on that, let's take a look at vector number 2. I'm going to erase this so that we have more space. So vector number 2, let's take a look. Vector number 2, I am actually having going down, starting from 10, 10, all the way down here. Now I move from 10, becoming a 3, actually become less on my x-coordinate. So I'm going to have a -7 on my x-coordinate. Now I start from the 10 on my y-coordinate and I go down all the way to -1. That means I actually move down by 11 for my y-coordinate. So putting a V-shaped bracket, I was already having a vector notation. But what about in physics? Well, I actually just turn it into a -7I with a hat plus a -11J with a hat. Now, if you don't want to put the plus, that's also okay. Just immediately delete this and leave the negative sign here. That's perfectly okay. Okay, so I'm going to erase it and write it better with just a negative sign right here. That will be fine. Okay, so 7, comma, and then -11J. Okay, now let's analyze vector number 3. Now I see vector number 3. Well, I'm starting from here, going all the way down to my left, down and left. So I start from a 10. I become a -1. So my x-coordinate is going to the left by 11. So I'm going to have a -11. And then my y-coordinate, I start from a 10, now become a 4. I went down by 6, so I should have a -6. In other words, I can have a -11I and then -6J. So vector number 4. Well, I have, starting from -1, +4, going all the way down to my left side, -2, -2. So, well, where's going to be -1 to -2? Oh, I'll just move 1 over to my left, so -1 to my left. What about my y-coordinate? My y-coordinate went from 4 to -2, so I actually went down by 6. Just like that, I have a -I and then -6J. Now, vector number 5, let's take a look at this. Vector number 5, I start from D all the way to C. That means I went from -1, 4 to 3, -1. So for my x-coordinate, I actually went positive. Went from -1 to become a 3, then I'm going to have a 4. Because 3 minus -1 become a 4. And then I went from 4 as a y-coordinate all the way down to -1, so I should take away 5. So I have a 4I and then minus 5j. Now again, I'm just keeping all the signs according to what I have in the vector coordinate vector representation, and then I'm going to translate into a component form. So again, this is just component form, and this is just regular vector form. Okay, so, but why is all of these 1, 2, 3, 4 is going to be helpful? Now here, I'm going to introduce a new concept for addition and subtraction. Now, anything that is following your vector, we're going to call it positive direction, regardless. We're going to say addition, and then anything that is reversing the vector direction, I'm going to say this is a subtraction. Now let's give an example. Now I'm going to change the color so that it's easier for recognizing. Now, in this morning, in our class, we actually talk about that, well, at vector number 3, add on to vector number 5, I'm actually equal to vector number 2. Why was that? Vector number 3, add on to vector number 5 is equal to vector number 2. Now, why was that? In our math world, if we're actually having a tail ending on a head and a head right here, well, I can actually make it as a connected path. I can went from A to D along vector number 3, D to C along vector number 5. That means my net traveling, it just went from A to C. Color right here, I just literally went from A to C. So based on this path, this is my regular path. And the red one, vector number 2, is my net. Now again, the word net in physics actually means that what does it actually do from the beginning to the end? Let's just take the shortest path. Let's just take a simplification about what we do. And then just how we describe net. Well, vector 2 is what we describe. It's a net right here. Oh, I first take the path from vector 3, and then I take the path by vector 5. Eventually, that makes me end up just taking vector 2 as a path. That will be easier. For example, this is like a park. If you need to travel from A point to C point, you can take 2 different paths. You can go from A to D, and then D to C. That's one path. And you can also take the shortcut, which is going from A all the way to C. Well, in the straight and exact path. So that means these two are going to be equal because you end up in the same exact beginning point and also the same exact ending point. Now let's take a look at another path. Now some other path right here also will end up in the same exact beginning and the end. Well, I can actually go from A to D, and then D to B, and then B to C. Well, this is exactly the same thing. Let's take a look. Well, I have vector number 3, add on to vector number 4, and then also add on to vector number 1 will also give me vector number 2. Well, why was that? Oh, look at this. I start from A, I go to D. I start from D, I go to B. I start from B, I go to C. Well, isn't that the same exact path I can just take from A to C? Well, in here, these two are the exact same thing right here. So I'm going to say that they're going to be equal. And that means also vector number 3 plus vector number 5 will be equal to vector number 3 plus 4 plus 1. Well, in here, that means by replacement, I can actually tell that vector number 5 and vector number 4 and 1 will be equal to each other. Well, let's take a look at why. And here, let me go ahead and change it purple. If I start from vector number 4, I went from D to B. Vector number 1, I went from B to C. Isn't that just exactly the same thing that you went from D to C? We're just taking the path for vector number 5. Well, this is just like, this is actually just like Prospect Park. Prospect Park for the botanical garden is exactly the same thing. You have a very long shape, and then there is a cutoff in the middle you can actually go through. This is how the botanical garden in Brooklyn gonna look like. Now here, all of these vectors are gonna be having the same representation. Same value, but by different representation. Well, I'm gonna prove it numerically. Why? Now let me go ahead and take away all of these highlighters. Okay, let's take a look at why was that happening. Okay. Okay. Vector number 5 still stays here. Okay, numerically, let's take a look. Well, vector number 3 and vector number 5. Vector number 3, let me just replace it by here. Negative 11, negative 6 by a vector. Add on vector number 5, which is right here. So I have 4, comma, negative 5 as a vector. Now let's numerically calculate it. Negative 11 and a 4. Well, that add up actually just to a negative 7. Negative 6 plus negative 5. That actually add up to negative 11. Well, hold on one second. Isn't that vector number 2 just exactly the same equation right here? Same vector representation. So numerically, we can solve it the same way. Let me go ahead and do another one. Let's go ahead and do number 3 and 4 and 1. Let's take a look if that's going to be the same thing. Well, let's write down vector number 3. Vector number 3 is going to be negative 11, negative 6. And then vector number 4, which is negative 1, negative 6. And then vector number 1 is 5, comma 1. Let's take a look. Well, I'm going to have all the x component add up together. That means all the i's add up together. Negative 11, negative 1, and positive 5. That means it's negative 12 plus 5. I'm going to have a negative 6. Then I'm going to add up all the y component. That means all the j's. That means where are you going to move up and down? Well, in here I have negative 6, and positive 1. That means, again, negative 12 plus 1, which is negative 11. Let me put back the bracket. Well, take a look. Vector number 2 is going to be the same thing. Oh, sorry, this is 7. Vector number 2 is going to be the same exact thing right here. Now, numerically, this is how we're going to do this. Now, again, addition and subtraction for vectors, you're just taking all the x component together and all the y component together. Now, let's take a look at this one. Now, Gabi asked me a very good question this morning talking about what if vector number 2 is a reverse direction? What would happen? Let me go ahead and draw this out. If vector number 2 is in this direction, vector number 2. That means vector number 2 is going to have a new component right here. Vector number 2 is actually going to be positive 7 and then positive 11. Why was that? Because I go to the right and I go up. That is going to be vector number 2. And all of these number calculations, I'm going to have a negative vector 2. Now in here, I'm going to replace my negative vector 2. Why was that? Let's take a look. I go from here, start from A to D, D to C. That is my regular path. That means I want to go from A to C. But the thing is, vector number 2 actually go from C to A. Now again, I've reversed my direction. What does it do? Oh, all I got to do is just I'll simply add a negative sign. So if I actually do change vector number 2 upside down, so I reverse, starting from end point to beginning point, and beginning point become the end point, that means all I got to do is just put on a negative sign, and then that will still be my equation. Just like that. That'll be my negative vector number 2. Okay? But when we're talking about a negative reverse following vectors, we're going to talk about it in 2 days later.